All right, question number 5. You should handle these problems very similar to the way you just handled the previous problem on number 4. Number 4, when you have like radicals that are being multiplied together, you can combine them underneath one radical and just simplify from there. We're going to do the exact same thing here. Notice that we have like radicals. The numerator is a square root and the denominator is a square root when you look at 5a. So it's okay to look at that as one square root, and so we're going to go ahead and do that. And we're going to look at that as just nothing more than just 36, the square root of 36x to the 16th divided by 3x. And so what we have to do apparently very carefully here, because as Mr. Cook has goofed this up a couple times in front of you, I apologize, is make sure that you are knowing your properties pretty well. And those properties consist of you making sure that you are very careful at making sure not only do you divide properly, wink, 36 divided by 3, but you're also using your quotient property with exponents, and realize what you have here is x to the 16th divided by x to the 1st. So 36 divided by 3, last time I checked, and I checked pretty recently, it is 12, and then x to the 16th divided by x to the 1st, subtract those exponents, and you get x to the 15th. So this one now we're going to split this up and kind of look at perfect squares that will go into 12 and perfect squares that will go into x to the 15th. Biggest perfect square that would go into 12, I think it would be 4, right? Because we could look at 12 as 4 times 3, right? And then we could look at x to the 15th as being x to the 14th. X to the 14th is a perfect square times x to the 1st. Remember, you're always going to want that largest perfect square. It's very easy for us, and we've practiced this quite a bit when it comes to the number, work with the numbers. But when you look at it with the variables, make sure you're doing the same thing there. I'm yapping too much. Let's get to the answers before I mess up again. All right, so perfect square here, perfect square there. We get square root of 4 times 3 times x to the 14th times x. I'm going to reorder those, that way we have the perfect squares lined up, and notice I applied the square root property, that product property. So now going in the other direction. Square root of 4 times square root of x to the 14th, which allows us to say that that's just 2x to the 7th. And then what we have left there is the square root of 3 times square root of x. We combine and right underneath one root. Okay? Good? Good. Let's look at these ones here. So simplify the equation. What makes this one different from the previous two problems of number 4 and number 5? 4, you're multiplying. Okay? 5, you're dividing. There's certain rules that we can use with multiplication and division. There are different rules. Very different rules when the name of the game is either addition or subtraction. In this case, boy, I wrote subtraction for all of these. But it wouldn't really matter whether it's addition or subtraction. The same rules apply. And that very important rule, and you already know this rule, some of you, is that you can only simplify like radicals. In other words, radicals have the same index and the same radicand. So, same index, same radicand. What does that mean? Well, same index, same radicand. We're looking at this guy right here. Do we have the same index? Yes, they're both square roots. Do we have the same number underneath the square root? Yes, they're both 3's. So what we would call these is we would definitely call these like radicals, and then we can combine those by just simply taking 4 of those square roots of 3's and subtract 2 of those square roots of 3's. And that would leave us with, you got it, and I think I might have, yeah, I think I wrote the final answer here. Yep, 2 square roots of 3. Now what do you notice here about this one, the one in the middle? We have a square root of 27 and a square root of 11. Ruh-roh. What we have here are not like radicals. So this one here is already simplified. Can't do anything with it. So I'm going to leave C to you. Take a look at that problem. Check your answer, either online or with Mrs. Regal. See if you can actually figure out if those are like radicals or not. And then if they are, combine them together. If they're not, tell me it's already simplified. Alright, let's look at number 7. Now, at first glance, do you notice this is very similar to the one we just did, number 6? We are adding and subtracting radicals together. And you might be very quick to say, ooh, none of these radicands are the same, so we can't simplify it. Au contraire, mon frère. Yes, we can. Remember, sometimes these radicals can be simplified, so we try to simplify those radicals first. So how do I simplify those radicals? You got it. Once again, we need that list of perfect squares. Excuse me, don't we? And so if we're looking at this, square root of 10, I don't even see any numbers here that would actually go into the square root of 10, so that could be a clue. Use that clue to your advantage. If you actually run across one that's already simplified, take that 10, and I don't know, let's take that 90 and divide it by 10. And what do we get? Oh look, we get 9. And that's going to be your perfect square. So we have 9 times 10. And then if we take the 250 and divide it by 10, what do you think we get? Oh look, 25. That is a cool trick that you can always use. In other words, if you spot one that's already simplified, use that, divide it by those other ones, and you can get the perfect square that you need. Okay? So, since that's the case, we can split this up into the square root of 10 plus 9 times 10 minus 25 times 10. Splitting all those radicals up gives us the square root of 10 times the square root of 9 times the square root of 10 minus the square root of 25 times the square root of 10. Notice I'm still keeping the perfect squares in green because then I can take the square root of each one of those, which would take that square root of 9 to a 3, that square root of 25 to a 5. Don't lose that minus sign there. A lot of students tend to let that minus sign disappear and kind of morph into an addition sign. Don't let that happen. Do you see why it's a good idea to put that green 1 right there? Just to remind yourself that you're taking 1 square root of 10 and adding 3 more square roots of 10 for a total of 4 square roots of 10. And then we're taking the 4 square roots of 10 and subtracting 5 square roots of 10 to put us at negative 1 square root of 10, which is the most simplified answer. If this is multiple choice, you wouldn't see that. You'd actually just see negative square root of 10. Notice the negative sign is outside the square root. Okay, so you have the same issue here in front of you when it comes to B. Look carefully at those. Intimidating numbers. Yes, I would agree. But look at that last one, the square root of 11. I don't think square root of 11 can be simplified, so use that same trick. Okay? Now let's take a look at these ones. Let's multiply some radicals together. If you guys can FOIL first, outer, inner, last, there's no reason why we can't do this. I remember from last year when I gave this problem to students, and then when we did this in lessons, students seemed to really struggle with this. But yet when I put, say, 6x plus 10 plus times 6x minus 10, nobody had any problem with it. It's the fact that square root right there is really thinks that students tend to think that the game has really changed. It really hasn't. Honestly, look at the problem the same way that you would any other problem where you're asked to FOIL. Okay, so if I have 6 plus the square root of 10 times 6 minus the square root of 10, you can set it up just like this. That's totally okay. Let me zoom in here a little bit. So then the first spot, upper left, that's 6 times 6, so wouldn't that be a positive 36? I have 6 times the square root of 10, a positive square root of 10, so let's write that as positive 6 square roots of 10. Down here, wouldn't that be a negative 6 square roots of 10? Now this is where it gets interesting right here. If I take a square root of 10 times a negative square root of 10, wouldn't I have a negative square root of 100? Doesn't that make sense? Because I have to multiply the 10 times the 10 together, because they're both underneath the square root. A lot of you in this room skipped that step because you realize that when you have a square root of 10 times a square root of 10, you really have a square root of 10 squared, and realize that a square and a square root are inverses of each other, and you're left with 10. If this was actually a negative, I'm sorry, I put the negative right there, it would just end up being a negative 10. Okay? So why don't we just treat it like that? And let's just call that negative 10. Now do you notice why I decided to put the 36 in blue and the negative 10 in blue? It's because those are like terms. Do you see why I have the green 6 square roots of 10 and the negative 6 square roots of 10? That's because those are like terms. You combine those like terms together, you're going to get 0 square roots of 10. And 0 times the square root of 10 would make 0. So all I really essentially have left here is 36 minus 10 for a grand total of 26. Does that make sense? Email me if it doesn't. Okay? See how B set it up exactly the same way. Exactly the same way. And you should be good to go there, because once again, what was that special name we gave these guys here again? Didn't we call them conjugates And conjugates have some really great properties, and that's this right here, is that those middle terms will undo each other. Okay? Now, let's look at these problems. Number 9, let's rewrite each expression as a radical expression and then simplify. What that means is simply change this one into a root and then simplify the expression. Okay? So a special note that I want everyone to remember here about changing these here, and remember that little analogy I gave you in previous videos. Roots are underground. In other words, what I mean by that is that the root is always going to be the denominator number. So when you see 64 to the 1/3, what you should really look at that as being is the cube root is 64, and the cube root of 64 would be 4. That's essentially what I want you to be doing here, right? So if we were looking at C right there, we'd be doing the 5th root of 32, which the answer would be 2. Okay, looking at number 10, simplify the expression. You've got 2 routes here. Here's one route you could take. You could use the fact that we can get, because we have the same base, 256 and 256, we can use an exponent property where we add the exponents together. The only hiccup in doing this method is, do you notice that we were trying to take 1/4 and add 1/2, and the problem is that we do not have a common denominator, so we would need to get a common denominator, and the common denominator would be 4, right? So 1/4 plus 2/4, right? So we could rewrite this one as 256 to the 1/4 times 256 to the 2/4, which would give us 256 to the 3/4. Now when it says simplify, if this problem is multiple choice, you might not see this as an answer. Reason why is because you might have to, you guessed it, have to figure out what the 4th root of 256 is, because roots are underground, and then cube that answer. And so then you might actually see 64 as an answer. Okay? The other method that I'll briefly talk about over here is that realize that, couldn't you actually just do each one of these individually? Take the radical first and then multiply. In other words, if I have the 36 to the 1/2 times 36 to the 1/2, isn't that really no different than me doing the same move that I just did right up here and rewrote those as radicals? It's really saying the square root of 36 times the square root of 36, and I think you guys know how to finish that problem and give me the final answer there. Okay? Be careful. Be very, 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 very careful. Okay? Alright, so down here on this last one here, and we'll pause this video and move on to the next level. So write the following exponential in radical form. I'm going to give you a exponent or a power with a rational exponent, in other words a fraction, and all I need to do, and all I really want you to do, the expectation, is for you to remember that those roots are underground. So I want you to look at x to the 8/5 and understand that we're taking the 5th root of x to the 8th. The reason why I wrote both of these here is I'll accept either answer. Either one is a perfectly okay way to write it, because in both cases you're taking a 5th root, okay, not a 5th power. Okay, the same is true over here with b. So do the exact same thing and you're good to go. Alright, so we'll move on to part 3 here.